All right, hello everybody. Welcome to EEE 135 Renewable Energy Systems. Here we're going to start Chapter 11, Water, Resource, and Energy. So first thing we need to talk about is what's the energy in moving water, right? So what does water begin with? Water is a molecule with two hydrogen and oxygen, kind of on the right, like so. And so the idea is this water is a very special molecule that could be in liquid form, solid form, or vapor form. Liquid is water, solid is ice, and vapor is steam. We're mainly going to be talking about the liquid part now. So why does water push you when you enter a river, right? If it's little molecules, right? One little drop of water is not going to do much, but a whole river, you might fall down, right? Molecules, even if they're invisible, have velocity and mass. And there's a force behind it, behind the molecule when it moves. So if you have enough molecules in water, it will collide with you and will push you in the direction of the water flow. Right? So moving water has a lot of force behind it. And then we thought a long time ago, how can we take moving water to produce energy? Right? Specifically, back in the day, we used it to turn a water wheel to do grinding or mechanical motions. But in today's world, we can make water turn a generator by turning a water wheel or a turbine. So the thing spins, connected to a generator, we can produce electric energy. And that's the whole reason why we're talking about this. When we want to talk about water, we need to talk about first potential energy of water, right? So remember, potential energy is energy at rest that's stored, and when released, will turn into kinetic energy and move, and we can harness that. Okay. So potential energy from water itself comes from the water wanting to move downhill due to gravity. Remember, water starts in the hills from the snow melting. It goes down the river through gravity, and all water ends up in the ocean. At the end of the day, water will always go down the ocean because that's sea level. That's the lowest point where the water can go. And then the water will evaporate into the air and it'll go back into the mountain. And that's a cycle of continuous water flowing from a river. Okay. So no water wants to flow downhill, and water high up in the mountain, a higher elevation, has potential energy to move down. And that's due to gravity. How can we calculate the stored potential energy of water? Well, very classic physics, you could take the mass of the water and the height that it's moving, it will potentially move, and then multiply that by gravity. So potential energy is going to be equal to the mass of the water times the gravity times the height in meters of how much it'll flow downhill. Okay. So quick example to show you the number crunching. You have a small reservoir of 8,000 acre-feet of water. Now remember, acre-feet of water is a very big amount of water. It's roughly 1,223 meters cubed of water. Now this 8,000 acre-feet of water is at an average height of 24 feet above us. So it's average 24 feet higher than us, which you turn it into SI units is about 7.32 meters. So the average height of the water is 7.2 meters above us. And then what's the total amount of potential energy stored behind the dam because they'll want to rush towards us and fall down. And then what is the average power release if the water is drained over 7 days? Okay, so if we let the water slowly drip out or move out of the reservoir over the course of 7 days, what's the average power? So first thing we need to talk about is mass. So we have volume, which is not mass. So we need to think about mass is equal to 8,000 acre-feet, which you convert to meters cubed, which is multiplied by 1,223. And then last thing we need is water density. The water density means for every cubic meter of water, so think of a cube, 1 meter by 1 meter by 1 meter, that weighs 1,000 kilograms. So we have a lot of water multiplied by 1,000 kilograms. Our mass of a reservoir is 9.86 times 10 to the 9th kilogram. So it's a lot, very heavy large lake behind this reservoir. Now we have mass, we could find potential energy. So we know potential energy is mass times gravity times height. We have all three of these, so it's number crunch it all. And we get our potential energy 707 times 10 to the 9th joules. So that's the potential energy ready to flow out. If we want to find the power, we take the total amount of energy divided by the time it takes to let all the water flow. And it's 707 times 10 to the 9 joules divided by 7 days, but when we multiply by 24 hours, and then we multiply it by 3,600 seconds. At the end of the day, power is joules over seconds. So we just unit conversion. At the end, you get 1.17 megawatts. So all that stored energy in that reservoir, you open the gate, let it all through over a course of 7 days, it can constantly produce, on average, 1.17 megawatts of energy, which we harvest to make electric energy later. Okay. So just to give you a good idea, 1.17 megawatts, you know what a megawatt is in terms of power. It's a pretty big unit for a household, but for utility, 1 megawatt is kind of small-ish, medium-ish, right? Typically, we need a lot more than 1 megawatt to power a city, right? We need like 1,000 megawatts to power a city. Okay, but we're starting from somewhere. Okay, so that's potential energy. Let's talk about kinetic energy next. So kinetic energy is when we open the gate and let all the water flow out. Okay. So what is kinetic energy? Where does it come from for water? Letting water move and push the water wheel and turbine. Okay. Where can you calculate the stored kinetic energy? Well, kinetic energy, because it's moving, you take the mass of the water moving and you multiply it by the velocity squared, and then you half it. So kinetic energy, very classic physics equation, is 1/2 times mass times velocity squared. Okay. Obviously, the faster the water moves, exponentially faster your kinetic energy is going to be. So you want to make the water as fast as possible. Heavier the water is, the more water flows through, you can get more power as well. Okay. So talk about the power in moving water. So how does the water reach the turbine to produce electricity down here? So we have the water uphill somewhere. It's kind of a river. We could put a little mini wall to kind of pull it up and divert some of the water. So we can force it to enter a turbine generator downstream by forcing it into intake pipe. And this pipe is called a penstock. Water will flow through the penstock, hit a turbine and generator, and it'll spin and produce electricity. So how does the water reach a turbine to produce electricity? You have a pipe called a penstock, helps funnel the water to the turbine. Okay? And then you let the water through the tail race and it goes back to the river and everything downstream is fine. How would we increase the power output of this dam? How do we make more power out of this thing? Well, you know kinetic energy is based on velocity. So if we can increase the water velocity, it'll increase the power, or we increase the volume of water, aka the mass going through the penstock. So we could somehow increase the water velocity, or we just make the pipe bigger to let more water through. One of those two things will work to increase the power. Okay. Now, let's start talking formally about a dam. A dam is a large concrete structure with a big wall to force the water behind it to pool up into a gigantic lake called a reservoir. We're going to let some of the water through. It's going to turn a turbine, which will spin a generator to produce electricity, and we let some of the rest of the water out and then to the afterbay, and it'll flow down to the rest of the river, eventually hitting the ocean, right? One of the key components to how much power a dam can produce is called the head. The equivalent head is 3 components of energy. The potential energy from elevation, meaning how high is this water level up here compared to where it's going out here. So this water difference, technically between the turbine and the top of the reservoir, this H is a potential energy from elevation. Another one is the potential energy from the water pressure. right? You have a lot of water up here pushing a lot of water down here, so there's going to be higher pressure here. And there's going to be pretty high pressure going to turbine. The more pressure, the more potential energy we'll get. And lastly, we need kinetic energy from the water actually moving. So we talked about how fast the water moves, you can have more energy. These three together, if you calculate the energy, you could get the equivalent dam's head, quote, and that's a direct correlation to how much power it can produce. Okay. How does changing the dam head change the stored energy? We kind of talked about it just now, but the bigger the dam head means more water volume mass behind the dam. More volume means more pressure. Gravity pulls the water down. You'll have more pressure and more velocity going through the pen side. So everybody wants a bigger reservoir. Everybody wants more pressure. Everybody wants faster velocity to make the dam go. And we try to make them as big as possible before it's unrealistic due to cost, size limitation, or just there's not enough water. Okay, this is why dams are typically really big, because we want to try to get the maximum amount of power out of it. Okay. So let's go through each one. Talk about the first one, potential energy due to elevation. This is very simple. You get your height difference between where the water hits the turbine and releases its energy here, and the very top of the reservoir. That height difference, you plug into your standard potential energy formula, which is energy equals mass times gravity times height. Okay. You know the mass of the whole reservoir, you could calculate that. You know gravity, that's a constant, and you know the height, you could figure that out. Okay. How does modifying this height change the potential energy stored behind the dam? The bigger or smaller this height, the bigger or smaller the reservoir, right? So it'll increase or decrease proportionally. I mean, at the end of the day, you have the H right here is multiplied, so it's proportional increase or decrease. So we make the dam shorter, we're going to lose some power. We make the dam taller, we're going to increase power, okay? Or energy. Another one is potential energy due to pressure, right? So think about the potential energy or the pressure at the top of the reservoir is low because there's not a lot of water pushing down from gravity. But the very bottom of the reservoir is very, very high pressure because all this water weight, mass, and weight is pushing down through gravity. So it's a very high pressure at the bottom of the reservoir. Okay. So how does water pressure change in the electric dam? Water pressure increases the deeper the water resides. How can we calculate the equivalent head from the water pressure? So the idea is, how can we, quote, make an equivalent? Equivalent just means placeholder. Variable to say how much kinetic energy changes based on the pressure. Okay. So we could calculate the head, P for pressure, head pressure is equal to the actual pressure exerted from the water divided by the specific weight of the water itself. Okay? And the specific weight of water is 9,807 newtons per meters cubed. Okay? Pressure is going to depend on how big the reservoir is. Okay? But as long as you know these two, you could get the equivalent head and then add that into the other variables we'll see to get our total equivalent head. Okay. The third one is kinetic energy due to motion. So remember, we got potential energy of the reservoir in the water. We're going to open the gate, let everything through, turn the turbine to turn the generator. So potential energy, once it starts moving, turns into kinetic energy. Once it hits the turbine, it turns into electric energy and goes to the grid. How does kinetic energy calculated? Well, kinetic energy is always equal to 1/2 mass times velocity squared, velocity of the water. Now, we need to get an equivalent head distance from kinetic energy. We could do a little math, little tricks. So on the left-hand side, we have kinetic energy is 1/2 mv squared. We know any amount of potential energy here can and will be transferred to kinetic energy. So in essence, kinetic energy and potential energy are the same, right? If we have 1,000,000 joules here, and we let it flow, it's going to turn to a million joules of kinetic energy as it starts moving, right? It's energy conservation. You can't take away or magically create more energy, okay? So we can equate these two. So you have this one equation, 1/2 mv squared can be equal to mass times gravity times height of the kinetic energy, okay? And then we cancel the m's, and now we have 1/2 v squared equals g times h of kinetic energy. This is equivalent head due to kinetic energy. So we cancel the m, and we just shove gravity on the other side, and the equivalent head due to kinetic energy, h of ke, is equal to 1/2 v squared over g. Okay, I mean, this is just physics and math tricks at the end of the day. The key concept here is all potential energy converts to kinetic energy, and we could just play around with equations to get an equivalent head right here, which is based on the velocity of the water moving and some gravity and some other shenanigans. Okay. So why are we doing this? We have three things: potential energy due to elevation, due to pressure, and kinetic energy. We want to add all these together to get an equivalent head to calculate the actual power of the dam. One of these three is not enough to calculate the total power. You need all three. So remember, equivalent head is equal to the actual physical height and the potential energy stored in the reservoir, plus the pressure exerted on the water, plus the kinetic energy when everything starts flowing. Okay. Now let's do some swap some equations. We know H of P is equal to pressure divided by the specific weight of water, and we know the kinetic energy, the head equivalent of kinetic energy is V squared over 2 times gravity. So this is your main equation to use. Now, once you know this variable, you could then calculate power down here. Power is always equal to energy divided by time, which, remember, energy of dam is always mass times gravity times height. But we're adding in the equivalent height instead of just the physical height, because we're adding in that pressure, adding in that kinetic energy component. So total power is mass times gravity times equivalent head divided by time, and you could just rearrange it with some brackets and make it look neat. But a big trick here is that equivalent head will help figure out power. So this bottom equation, if you got all these variables, you could directly connect this, calculate this. Now, a lot of times when you're doing fluids, you might go by volumetric flow rate rather than just velocity up here. Okay, so the water is moving, you could calculate power directly by volumetric flow rate. QV is always in meters cubed over squared. So every second, you're calculating how many cubes of water is flowing past this pipe. It's kind of like current, except instead of checking how many electrons flow through, we're checking how many gallons of water is flowing by, right, at the end of the day. So basically, how much water flows every second. Now you could calculate QV pretty easily. It's the mass of the water times gravity divided by T, which you already have right here in the power equation. Okay, so it's easily just to copy and paste these things through. And so your total power here will be the density of the water times your volumetric flow rate times your equivalent head. Okay. And with this, we could then calculate the total power based on volumetric flow rate. Okay. So let's go ahead and do a quick example to calculate the total power of the water behind a dam. So let's say we have a small stream. We have a little mini dam on the stream. The stream has a head of 8 meters from the top of the penstock pipe to the bottom of the turbine. So the height difference is 8 meters. The volumetric flow rate is 0.05 meters cubed over seconds. Calculate the total power available to the turbine. Okay. And maybe let me add this thing real quick. Let's say equivalent head, just to make things make sure we there's no mistakes. Okay. And I think, yeah, we'll go with that. So here, power is always going to be equal to, sorry, the specific weight of water. I think previously I said the density is specific weight of water. My apologies. Okay. Times your volumetric flow rate times your equivalent head. So specific weight of water is 9,807 units per meters cubed. The flow rate is 0.05 meters cubed per second. So you can see the meters cubed cancel. And then you multiply by 8 meters. So power would then be Newton times meters over seconds, which SI units check out. So we have 3.92 kilowatts of power. Okay. So as long as you understand what each of these variables mean, and you could get those numbers out, I mean, at the end of the day, this is just number crunching. Okay. So with that being said, let's go ahead and do an exercise. Again, I'm going to say an equivalent head. Right. So we have a small stream equivalent have now 10 meters from the penstock to the tube. The volumetric flow rate is a little bit bigger, is 0.06 meters cubed per second. Calculate the total power available to the turbine with a penstock power loss of 20%. So what this part means is you will calculate your total power, and then you're going to lose 20% of that power as it flows through the pipe, because the pipe's not perfect, right? It might bend a little bit, so every time you bend, you lose some power. It might be some, it might be crimpled or something. Who knows? But pipes will always have losses. So whatever power you have, chop off 20% of that loss to go from ideal power to more realistic power, and that'll be your total answer. Okay. Obviously, the 10 meters is bigger, the flow rate is bigger, so your total power should be more, but then the penstock loss will kind of chop it off a little bit. Okay. So let's take our 15 or so minute breaks, do this calculation real quick. We'll come back, see how you did it, and check your answers. Okay. So we'll see you in a second. All right, hello everybody. Welcome back to EEE 135, where we're going to continue our exercise 1 for chapter 11 on water energy. So remember, we want to talk about calculating the total power loss, including a penstock power loss of 20%. So first thing we should do, calculate the power. Power is equal to specific weight of gravity times the volumetric flow rate times the equivalent head. Just a number crunch, basically. You get 5.88 kW. We're going to take a 20% cut or hit in power, so we're only going to get 80% out. So our true total power is going to be 4.71 kilowatts. All right. So just first half of the course, just doing some lecture, doing some number crunching. Now let's go start talking about the types of hydroelectric dams you will encounter. Okay. First one you're going to see is a dam that has a very large reservoir, a very high head, very big. It's called a conventional hydroelectric dam. This is probably the thing that most people envision when they see your hydroelectric dam. Another type is a dam that has two reservoirs. They can pump water in between each one. This is called a pumped storage dam. A third type is a dam that is installed along a running river to capture the kinetic energy of the water flow. This is called run-of-the-river dam. So note that this type of dam does not have a giant reservoir lake behind it. It's only there to capture the kinetic energy as the water flows. Lastly, we have much smaller versions of the previous dams on rivers and small canals, and they're called small or micro hydroelectric dam. Okay. So we're going to go ahead and talk about each one, kind of give you some images and just try to figure out how it works. So standard conventional hydroelectric dam, you get the main concrete wall with a reservoir behind it. You got a screen, you got the penstock, turbine, generator, powerhouse, step-up transformer to the main grid. After the water comes out the turbine, you have a tail race or exit pipe, and it goes to the afterbay and it flows more downhill to the rest of the river, eventually to the ocean. What's the function of screen, gate, and penstock? Well, the screen stops fish and objects from entering the penstock because you might muck it It might get stuck. You might damage the turbine. It's the blades itself. So you want to make sure foreign objects don't come in. So think of it like a filter. The gate will control water flow going into the penstock. Sometimes you want a lot, sometimes you want little. This is basically control the amount of power to the turbine, also control the power to the generator. Okay, so it's very important to have a controlled power. You don't want to put too much power out to the grid if you don't need it, but you don't want to put too little because then the generator starts motoring and that's really bad. So there's a very delicate balance between the power going from the turbine to the generator, and the gate opening and closing will help balance that power. So the gate controls the water flow. The penstock itself funnels water to the turbine, and then it'll spin the turbine. What's the function of the turbine in the middle, the generator, and the powerhouse? So here, the water enters from this penstock, spins a turbine mechanically, so it's mechanically spinning pretty fast, I might add. And this turns the generator to produce electricity. Electricity comes out as 60 hertz, constant frequency to the main power grid. And then both the generator and turbine are installed in the powerhouse so that we keep, it should be very dry, no dust, no contaminants inside this building to make sure the generator lasts a long time. What's the function of the tail race down here in the after bay? Well, it's mainly the exit for the water to flow out of the turbine. You want to make sure this exit is very smooth. Otherwise, the water will start having back pressure, which will slow down the water coming in. So you got to make sure the tail race is very smooth operations for the water to flow out. You have to after bay here to collect the water so it can kind of settle down. You don't have these crashing waves everywhere. And then once it smooths down, it'll go to the rest. It'll enter the river and start flowing downhill to the farmlands, to the cities, and eventually to the ocean. Okay. So very conventional look of a hydroelectric dam. A lot of them have very high heads. This could be like 50 meters high. Really big reservoir behind it. The obvious one you probably know is a Folsom Dam, not too far from Sac State. So you see you have a very giant reservoir behind it. Then you have the dam itself. You got some gates where it could open. You got these 3 pipes, and you got the powerhouse down there. So down here you can see that you got the main lake. You got some sensing device up here, but the main thing is right down here, these 3 pipes. These are the penstocks that we're talking about. So you have openings down here at the dam. Water will flow. It will eventually come to this powerhouse. Because there's 3 pipes, there's going to be 3 turbines, 3 generators that will go to the lower after bay here down to the American River and flow towards Sacramento and eventually San Francisco and all that good stuff. Okay. You also have up here these gates. These are overflow gates in case there's too much water. Instead of going to the penstock, you can overflow and bypass the generator because you don't want to put too much water in the generator. You might overburden it. So just in case we have too much water, like it rained too much or too much snow, this is a good bypass feature. You can kind of see right here, they're opening the bypass to let the water through. Okay. Other thing you should note is look at the distance, the height. So the after bay is down here. The dam, top of the dam is up here. So there's a pretty big 50-meter difference, I would say, right? So that's a lot of potential energy behind the dam. Another thing to note is the width of the dam is not that long. The reason why they installed it here, because it was a natural kind of like bowl shape of terrain features. So all you had to do was build one wall here to encapsulate this whole area and turn it into the reservoir and lake. Okay. Why do we need a large lake reservoir? More water means more water mass means more pressure. More pressure produces more power per volume of water you let through. So we always want more pressure, more power, right, for the same amount of water. The higher the dam, the better. Okay. And they chose this height because this is probably the limit of the rest of the terrain around the bowl to make the reservoir. You don't want to make this too high because then the water will spill out somewhere else and they're not going to get redirected to your dam. Okay. So that is your standard Folsom Dam. Next one we're going to talk about is pump storage dam. So this is kind of more specialized idea where we'll have a lower reservoir and then an upper reservoir. We'll have this tunnel slash penstock right here. We'll have a second one down here. And then we'll have the generator pump, either let water from the upper reservoir down to the lower to generate power, or if we have too much power, we could take power from the grid and run the generator as a motor, because electric machines could be generator or motor. All the difference is which one has more power. If the mechanical side has more power, it's a generator. If the electrical side has more power, it's a motor. So we're going to take electric energy, pump it into the machine to turn into a motor, and we'll actually take water from the lower reservoir and pump it up to the upper reservoir. It takes energy to do that, but then we could store it as potential energy for later use. That's why it's storage. What's a function of pump storage dam? To store energy from the power grid as potential energy for later use. Right? How do we store electric energy from a power grid? Run a motor to pump the water uphill to the upper reservoir. And then how do we release electric energy to the power grid? It should be two. Sorry. Is release water from the upper reservoir down to the lower reservoir, and it will run the electric machine as a generator and send power to the main grid. One would ask, why do we ever want to take power from the grid, right? There could be times where we have too much power, because remember, at the end of the day, the grid, you need balanced power generation and power loading. Let's say there's a sudden drop in load, or some generators must stay on. Perfect example is, what if it's really sunny? What if we have got PV power going on, but we have too much? We can't turn off PV systems easily. So instead of just wasting it, let's put it into this pump storage and absorb the power. When can we release the power? Well, what about at nighttime when the sun's not out and the PV panels are gone? They're not producing energy. That's a perfect time to release the power back into the grid. Right? So think of it, pump storage is a gigantic battery to absorb energy and release it when we need it. Okay, really good system. Right? The most famous one in California is called Helms Pump Storage Plant. It's actually, I believe it's 2 hours east of Fresno. So it's kind of in the Central Valley. Not too far from where I live, because I live in Turlock. So here you have the upper reservoir called the Courtright Reservoir. You're going to have some underground piping to go down to the turbine right here, and the generator. And it's going to pump out to the lower reservoir, the Wishon Reservoir. And then it's all about pumping water uphill or letting water flow downhill to release energy to the grid or absorb energy from the grid. It's one of those two. Okay. Down here, this is kind of a topology map. So you can see that they're within close distance to each other, not too far, not too close, but definitely you have two naturally occurring reservoirs. So this is an ideal location to build it. What are physical requirements for building a pump storage plant? You need two reservoirs near each other, and you have to have a large elevation difference. If both water-based reservoirs are at this equal level, you're not going to get any much power pumping or letting water through. It's going to be very little because your height difference isn't much. Here, you got a high level water head. You got a low level water here, so the difference between up here and down here, that's a potential energy stored, which will be eventually turned into electrical power. Okay, so very good system. These are the 3 units. So you got 3 main electrical machines. These either run as generators or motors. And then below it is a turbine. Okay. Now don't mistake, these 3 pipes are not the penstocks to let the water through. There's no way you're gonna have this 90-degree bend for water. They'll never let that happen. These are the 3 cables from the generator out to the main power grid. It's going to be ABC, ABC, ABC phase, right? And then this goes to the main switch yard with a GSU, a generator step-up transformer, and that goes to the main power grid. Okay. But this is typically what the 3 generators look like, and then well below it is the actual turbine. Okay. The third type we're going to talk about is run-of-the-river hydroelectric dam. This is where you have a pretty big river with moving water. And then we're going to build kind of a little mini dam, not too high, maybe like 5 meters, 10 meters maximum. Probably not even 10 meters, more like 5 meters, right? And then you're going to let the water naturally divert, and we're going to kind of build a secondary river out here. And then that's going to go through eventually through a penstock to the powerhouse. So you're basically diverting the water around the main river to force it through the powerhouse to make power and then let it return back to the stream, the main river. Okay. So where do we install a run-of-the-river dam? On a large volume river. So the river needs to have a lot of water flowing through for it to make economical sense. How does it make power? Divert some of the river water flow into the powerhouse to run a turbine and generator. One thing to note is you still need outlets for the water to flow directly through the river itself, because you don't want all the water to flow through the powerhouse because you might overwhelm it. Okay, so there's always going to be kind of a balance of how much water flows through the river versus what you divert. Okay. The big thing here is that the height difference is not much. There is no real reservoir behind it, so you don't have a lot of pressure, you don't have a lot of height, so you're not going to really make a lot of power, unfortunately. Kind of example to show you a run-of-river dam, Chief Joseph's run-of-river dam. And notice you have the main river flowing through. Main water is going to, some of the water is going to flow directly through the gate and go through. We're not making any power here, right? Some of it might get diverted over. And then probably off screen somewhere, there's going to be some pipes and a generator, maybe down here, that will then let the water flow back in. Okay. So not a big reservoir behind it. Height-wise, maybe 10 meters high, not too much compared to a main conventional dam. Okay. So compared to the conventional hydroelectric dam, was a run-of-river dam missing? Again, large reservoir of water, no pressure behind the dam, or very little pressure behind the dam. How does it affect power generation of the run-of-river dam? Very little pressure in the water flow. It reduces the power output per volume water flowing through the dam. Okay, so you have to flow an insane amount of water through this dam to make power compared to a conventional hydroelectric dam. Okay. Now, if you have a very big river with a lot of flow, you can't get up there. It is possible. Okay. One asks, why not just build a regular dam? Why build this instead of a conventional dam? Mainly because you don't want to waste the space behind it and turn it into a reservoir. Reservoirs are big. What if you have towns and farms here? You don't want this to flood into water, because then you'll lose those people who have to move. They'll get angry. You'll lose farmlands. So there's some logic in using a run-of-the-river dam instead of a conventional hydroelectric dam, right? It's just you don't want to create a giant lake behind it, right? Or you might not have the geographical nature. You might not have that nice bowl to make the water lake to begin with. Okay. As you see for hydroelectric dams, the natural topography of the land will dictate what type of dam you use more than anything else. Right? It's not economically feasible to just start moving billions of tons of dirt to make a dam. It's just not. Right? Just do it where you can and just enjoy it. So, last type we want to call or use or look at is a small hydroelectric dam. Okay, so these are much like mini versions of the regular dams, to where a small hydroelectric dam is under 10 megawatts to 100 kW. Okay, and then a micro dam is 100 kW or less. Now remember, 2 kW is about the size of a household usage. So 100 kW is maybe 50 houses or maybe a medium-sized neighborhood. Okay, so if you have a very small village of maybe a couple thousand people, you might be able to make a micro dam and use that to power that small community. That could happen. But don't expect these small dams to power a whole city. That's just not, it's too small. Okay. What type of dam structure is these small micro hydroelectric dams? They typically run at a river type because it's too expensive to build a conventional dam for such a small power output, right? No one's going to waste $100 million to build a 1 megawatt plant. That's just economically unfeasible, right? I'd rather spend $100 million to build a 100 megawatt plant instead, right? So kind of a small image of you got a little river, right? It's going to flow through this gate and flow down into this little funnel. And this is where the generator is to produce power. And it's going to go out here and keep on going. You're going to have a little diversion. This is kind of an emergency chute in case we have too much water here and the generator is not taking enough. We could divert some of the energy on the other side. Okay. So it's kind of like a bypass. Note this particular one doesn't have any gates, doesn't, or it might have some. They're just barely open. I do see a little water flowing over here. Okay. So overall, this is really small, though. I mean, you could tell. Look at the grass right there. If you could see the grass blades, you know this is small. This might be less than 10 feet, right? You know, so pretty small if you ask me. So what's a real life example of this? Where I work at TID, we do have small hydroelectric dams. This is what they look like. So just look at the truck in comparison. I mean, this isn't that big, right? Maybe 2 or 3 trucks length, and that's the size of the whole entire dam. This one's a little bit bigger down here, but still, look at the truck. It's not that big compared to a huge dam that's, you could probably put 50 trucks in a line for what Folsom Dam looks like. Okay. What type of water sources is does this small hydroelectric dam use, or what type of water source is this small hydroelectric dam installed on? Well, there's 2 types. One is a canal. So this is the irrigation canal we use to send water to the farmers. We said, let's put a little dam here. Might as well get some free power out. And it's true. Those water's going to flow down here, and then it's going to exit over here. You see how this little white ripples? This is the splash of the water falling out. It's going to keep on moving. It's going to continuously produce a little bit of electricity. Not much, but it's free. It's something. Okay. Down here, you're going to have a lake behind it. So we have a small lake, right? Water will enter it. Water, it's going to rain. This is going to be the runoff to the lake. And it's going to, instead of just let it pass through to the main river, let's put a little hydroelectric dam to produce a little bit of energy. Not a lot, but again, it's free. Might as well. Okay, so that's what small hydroelectric dams look like. So, what are the pros and cons for this traditional hydroelectric energy? Well, the big pros for hydroelectric energy, sorry, typo, hydroelectric energy. Yeah, let's do this. All right, there you go. Sorry about that. So pros of hydroelectric energy are free energy from water moving downstream. I mean, it's free. I can't argue with free. Big one, it offers flood control for downstream. So 100 years ago, Sacramento just flooded every 10 years and then downtown was underwater. So flooding used to be a very big natural disaster that killed lots and lots of people. So building a hydroelectric dam lets us control the water flow downstream so we don't have natural disasters anymore, right? So that's really good. Flood control is great. Another thing is you make a reservoir behind the hydroelectric dam, and you could be used as recreation. So a lot of times when you have a dam, you get the big reservoir. That's where a lot of people like to come, have sailboats, water skiing, and all playing around in water. Everybody likes on Folsom Dam, right? You go play around and have fun. So it's like artificially making a lake for recreation, which people like. So every dam will always have that nice recreational area behind it. So those are the pros. I mean, they sound pretty good. Now, of course, we got to talk about the cons. One of the big cons, it cuts off any boat traffic on the river. So if you're trying to take material from upstream to, let's say, up into the mountains, That dam blocks it. You're dead in the water. A boat cannot go up the dam. It's impossible, right? So all boat traffic is gone. All commerce, industry, that's not going to happen. This is why we don't have a dam from Sacramento down to the Bay Area, because that's a vital waterway for industries and commerce. It's not worth putting a dam. So you don't dam up vital waterways. You put a dam on not important waterways for electric energy. Okay? But it's a con for sure. Next, it stops fish from migrating. So there are some fish that want to, excuse me, go upstream. They jump upstream to lay their eggs and procreate and produce offsprings, and then go back downstream. Okay? So by putting a giant dam there, the fishes can't move upstream. They're going to die. Okay? That's a big con. Specifically in California, we have to make waterways to let the fish bypass the dam to go upstream. Right? There's a huge legal battle between animal activists for fish life versus making hydroelectric dam for power. And there's always a big battle back and forth of who's right. Another one, it stops river silt from fertilizing downstream. So throughout history, farmlands always needed water to grow effectively. And a river going downhill always took the minerals from the top of the mountain and brought it to the bottom basin where you had this nice fertile delta. So right before it hits the ocean, there's a large area where the river is. It's a lot of really good soil to make a lot of farmlands to grow produce. Okay, so this has always been a big pro for owning land near river or establishing a city near river, is you could produce a lot of food. But a dam stops that river silt from going downstream. Again, you're putting a giant wall. It's bad enough that the downstream farmers don't get their fertilizer anymore, so they have to use artificial fertilizer. It costs more money. It's not as healthy. The river silt actually will pile up behind the dam wall. If it gets too much, it'll actually start going into the penstock. So every couple of years, you have to go and dig out all the dirt and silt behind the dam and displace it. So it's a big issue. So you're trading all this pros for pretty much screwing over the farmers. I mean, let's be real. And reducing the agriculture industry. Okay. Lastly, very, very rare, but there's always a chance, you can have a dam breach. When a dam breaches, water will rush through the valley and we'll have mass flooding and people are going to die. It's going to be crazy. Recently, we had a big scare. If you remember a few years ago, you heard of the Oroville Dam up north had too much water, and water started flowing on the side through its bypass channel, and then it started breaking down and deteriorating. And they were afraid the whole dam was going to collapse because the water is breaking down the foundation. And they evacuated everybody at Oroville and said, you need to leave. You might not have a house when you come back. That was a scare of a dam breach. And we take it seriously, right? But hopefully this is like 1 in 100-year event. But definitely it's a con that we always have to prepare for in case this happens. Yeah. So in summary, water energy. The biggest impact of power generation for hydroelectric design is always going to be the head height. The taller the dam, the more equivalent height head we have. So more pressure, more kinetic energy, or the actual just the height is bigger, we're always going to make more power. So as long as one of those three goes up, we're always going to have more. Okay. Power of the water in a hydroelectric dam can always be calculated by power is equal to specific weight of water times the volumetric flow rate times the equivalent head. Or, if you don't want to use these two, power is going to equal the mass of the water, all the mass of the water, times gravity divided by the time it takes for all the water to pass through, times the equivalent head. There are 4 types of hydroelectric plants we use. Conventional hydroelectric dam, by far the most popular one, also the oldest. Pump storage dam, very neat, kind of rare, but if you can install it, it's pretty good. 3, run-in-a-river dam. This is smaller, but you sprinkle them everywhere you can. And 4, small hydroelectric dams, which again, if it's convenient, install it, get some free energy, and I'll be happy, right? So this is kind of a summary for today of just welcome to water, energy, and convention, the standard hydroelectric dams we use on waterways and reservoirs. We'll come back on the next session for this week where we'll start talking about the actual turbine and different models of the turbine, and then other types of water energy sources from the ocean we can harness as well. Okay. So hopefully everybody had a good day today and watching the video, and hope you guys have the rest of the night to be good as well. And we'll catch you next time. So have a good one. See you around.